Partiti? So this time, Nicoletta, you cannot complain about anything, not only we give our greetings, but we... giusto, Steven non c'è, possiamo parlare italiano. Non so, però questo lo facciamo... no, Steven. Ok, qui dobbiamo parlare di... Not only we give our greetings, but we also have a proof, a written proof of our love. Okay, so today's finally we start the theory of classical superalgebras. But before we start, I wanted to spend 5 minutes on the question of Fabrizio, because I wanted to think about it, but then on Thanksgiving I always call Varadaraja to say Happy Thanksgiving, so I called him and I figured, why not ask him Poincaré Birkovic? And he says, I asked, can I ask you about Poincaré Birkovic? And Varadaraja says, of course. It's a typical Thanksgiving conversation. So he says that your question could be motivated, but in fact is not motivated. No, because I explain what he says and I agree, but he made me think that you had a point. So the question is the following. You're looking... No, this chalk is awful. But there is nothing better. Vediamo questo. Maybe this one. So, a note... No, this one is slightly better. So the question that you are asking is that we first permute this one, and then it was this question, right? And you need to know this fact, right? Isn't this your question?
But it's not that you need to know it. You need to know that these are enough.
Yes, but the Varadarajan answer is that we devote quite some time to prove that there is an action of the permutation group on the tensors, and that this action is well behaved with respect to the sign. So since we have this action, your question is not substantiated because we already discussed this in the previous. So the point is, had we not discussed the action of a permutation group on tensors, you may be asking this question. But since we already discussed in detail that the tensors and tensor have action of the permutation group, and in fact these relations we verified to the uttermost detail, especially the sign. You remember there is this question on the sign.
Yes, but it was not the same action.
It is the same action. You are permuting, no?
No, in this case you are using this map from the tensor algebra to developing algebra. Maybe.
No, I think I did not think about it, but then it made me realize that it is important that you know that when you act on the tensors, you actually have this verified automatically because there is an action on tensor algebra.
But if this is automatic, you don't have to prove anything. Why did you verify this?
We verify this?
Yes.
We verify this.
But last time, what did you prove last time?
Okay, maybe I don't understand your question. We have a private conversation because I thought the question was the action on the tensor. Maybe I did a mistake.
First, I think that his point was the same in the classical and in the supercube.
Yes, it is a point that is, yes.
Between them. But on the other hand, I think that the proof, the point of the proof is that you have a definition by recursion.
Yes.
In his point of view, he thinks about applying, going on to apply, and then he said, well, you have to know that all the different ways that you can go through can be realized by switching of them.
Okay, so it is
No,
not
no,
action on the tensor.
no.
Yes.
But it looks like in the proof you don't take that point.
Yes, you don't take that.
You just say that you want to prove that the definition is well behaved when you go one step down. And that by induction you get that
Yes,
on the lower level of the induction it is well defined. It works. Maybe.
I'm sorry, I understood your question in the sense that when you permute the three objects, you must be sure this thing holds, and this is...
No, that was not.
No, but this has to hold, of course, right? No, but this has to... I thought this was your question, but I'm sorry, I did not understand it properly.
And so, in order to go one step down, you have only two ways of going.
No,
One step
No,
down.
you have many
There
ways.
are many ways, but you prove that if you go, for example, if you permute two things here, and you write down the definition of the quotient going one step down, and you permute two things here, then you compare the right-hand side, and using the fact that the function is well behaved, is well defined one step down, you can prove that they are the same. You also use linearity, math, that is one important factor. You are not, it's not completely combinatorial, it's combinatorial algebraic. You use also the linearity of the math. It's a different, they are connected, but it's a different point of view, and
Yes,
looks
but-
like it is correct.
What we did, we went one step down in two different ways. But then, why just two different ways and not many different ways?
Oh, yeah.
This is my question. So there are only two different ways to go down.
No, there are many different ways. You have two cases.
Only two cases to different.
Oh,
That's
three cases. Three cases.
And that's what
You start permuting one thing to. You start permuting to adjacent vectors, and the cases are, if you start here you permute two things, and here you permute two vectors, and they have no vector in common. This is one case, and you prove that then it is well defined. And the other case is that you start permuting two vectors, and the other two vectors have one vector in common. These are two. But maybe we can talk together another moment.
No, I think we should resume the discussion later among us, because
Yes.
otherwise, no, I'm sorry, because we want to...
No,
No, thank you. And I understand the point. I will think of it.
Okay, so we take a Lie superalgebra. I remind you that in where we field the K of characteristic different from 2 and 3, and we are in the case of finite dimensions, even if this makes sense also in infinite dimensions, but this is our framework for all our discussion. So we did in the past, but I wanted to quickly recall what is derived series. We take the first element of the derived series equal to G, and then we take a bracket Gi as the element I plus 1, so it's defined from step 0, step 1. So, and similarly, central series, we want this Gi plus 1 to be Gi. So G is solvable if and only if derived series end. What does it mean, derived series end? It means the same thing it means classically. So you start, you see, with G0, and then this contains G1 and so on. At some point you get to 0. Okay, so these are all one inside the other, and you want this to end. Is contain or equal, of course. And same thing for central series. What are examples of these algebras? So for example, classical example, you take G equal, for example, the matrix algebra, GLN, and what, sorry, we use G for the, we take a G inside the GLN, the set of all triangular matrices, so matrices like, it's like A11, AN, A12, and so on, 0 here, and if you make the calculation, is a very simple calculation. You see that every step that you take the bracket, this will become 0. So G1 is this 0, 0, and then something here, 0 here, and then G2 is a very simple calculation I invite you to do. So you have 0 here, and so on, and so it will end. So this is an example of solvable. And if we take n as and then here whatever, this is an example of nilpotent. So this is nilpotent. You cannot read that, okay? I will not write. And again, you can verify the same. And another example of nilpotent is when you take, okay.
That's classical.
But the same as non-classical.
Same as.
Yes, so if we take, so the example non-classical is GLMN, which I remind you are all the matrices of this type. And these two examples still will give, and I urge you to do the calculations for both. It's a simple exercise, but it is very, it is very instructive, this little exercise. Notice that nilpotent implies solvable because it's a stricter condition. Nilpotent also, for example, not only this, another example of nilpotent is when you have an abelian, for example, the diagonal matrices. So another example, say n prime is the prime is bad because it's with n tilde, is the diagonal matrices. If you take bracket, you get a 0 immediately. They commute. So this is so all abelian are immediately nilpotent, and of course solvable also. It's kind of a degenerate case, but it's important. Okay, so we have this notion. Solvable is very important in the theory of Lie algebras. In the theory of superalgebras, there is some twist. It's not, I cannot explain now, but let me tell to the people that know some Lie theory, which should be all the students that took the course. So, if you take solvable, containing all the solvable containing the same Cartan are conjugated by the action, adjoint action of group. It's important result. In the case of supergeometry, this is not true. So this is just a preview. What is the importance of this fact? As I will explain next time, because next time I want to say something about representations finally, solvable in some sense controls the representation. We will explain in which sense. So the fact that all the, to study representation you need to fix Cartan, and then you need to look at the solvable. In the super case, it's the same, you fix Cartan, except that it's not enough to look at one solvable. You need to look at all solvable that are not conjugated to this one, because in the classical case, they're all conjugate. So essentially, they're all isomorphic. You can go from one to the other, but here, no. So you have to take a different point of view. So this is an important difference, but I will explain this. It's just saying there is. Then G simple, finally, this Let's put here so the people will see that there is the seminars at least we wrote. Okay, we want to study simple Lie superalgebras. What is simple? So we want to exclude the case that G is abelian, and G contains no non-trivial ideals. So I need to say non-trivial because of course G has the ideal 0 and the ideal itself. These are always there. So I'm saying that there is no ideals except the obvious ones. And we say also that G is classical simple if it has a further property that, so G so we know that G0 acts on G1 through the bracket. So if G1 is a completely reducible G0 module, I try to explain. So we know that G0 acts as a no, because I remember that it would be nice to have a counterexample here to this property, but I forgot it to mention. So what does it mean, G1 to be a completely reducible G0 module? It means that I can write a G1 as a direct sum of, say, V1, V2, Vn irreducible G0 modules. Okay? So the action is the bracket, of course. There is no other action. Now, there is a classification of simple and classical simple from which one sees that G0 is a sum of simple algebras with some, there may be a center, but it's not important because the center acts trivially. So we are sure, I mean, if we know already the classification, this fact is obvious because you see, if G0 is the sum of simple algebras, we know the simple algebras over a field of characteristic 0, which is, say, over the complex field, the classification is over the complex field. The action is, as always, this property. But of course, you define it before knowing the classification. So, you see what I mean? I mean, if you already know the examples, it's obvious, this fact, but you don't know the examples. Okay, so I now want to give examples. Today I wanted to discuss the example of SLMN, which is classical simple, and OSP, because this, let me write a remark. We have in the classical setting, so if we talk about the Lie algebras, we have simple Lie algebras, right? Same concept. Simple Lie algebras divide in 4 families. So let me recall briefly this. So if G is simple Lie algebra, G is equal to one of the 4 family, AN, Bn, Cn, Dn. And then there are the exceptional. This is so F4, G2, what is it, E5, E6, 7, E8. Did I forget anything, Fabrizio?
There's one more. E5
There's one.
doesn't exist.
E5 does not exist. See how much I know about exception. Okay. So if we have a simple Lie algebra, G belongs to 4 infinite families plus a handful of exceptional. But the simple Lie algebras actually come from 3 classical groups. Precisely, A is the family of the special linear, B and D are the orthogonal, special orthogonal, doesn't matter, it's the same, special orthogonal, and C is the symplectic, okay? So actually there are only 3 corresponding to these 4 families, because so B is the odd special orthogonal, D is the even special orthogonal. So it's, you're doing the classification, right? Have you done it already?
No.
Not yet, but you will do. Now what happens here? Here we have a situation which is similar, because we have some families A, B, C, D, similar. Then we have exceptional. Then we have something more that I will explain. So today I want to give examples of the corresponding to these ones, okay? Today I want to give examples and then next time I will describe the exception, the corresponding exceptional, I don't care. There is also in the supersetting exceptional, but I don't want to go into this. I want to describe other 2 families that appear besides the BCD, which are the P and Q family that are called the strange. I will talk next time. But today I want to give the equivalent. So here they come from 3, SL, SO, SP. In a super case, they come from 2 superalgebra, SLMN and OSP. So they will give rise to the family A, B, C, D super. I will do all the details, but just to tell you. So this is why we are discussing these 2 particularly. Now, I want to prove that what I described is simple, so I need a result. It's similar also in the ordinary case. I need a result that tells me when an algebra, superalgebra is simple. Because it's not that you look at it and you see this. Usually it is hard to discover that something is simple. So I'm doing this result from Mousson now. Okay. So we need this lemma to prove that SL and OSP are simple okay, when they are simple. So I take a Lie superalgebra, always. So I think that now when we discuss the problem of classification, I think I feel more comfortable if we have over the complex field, because when you speak about completely reducible, all of these questions are better seen algebraically closed. But the truth is that you could give this definition in general, not necessarily over the complex, but if you look at Katz's paper, I think Mousson is also over the complex, but I'm not sure. So I take a superalgebra. G is simple. I think that now is not necessary, but it will be soon. If and only if we have 3 properties. First is they're very strange. So if I take an ideal which is non-zero, no, not an ideal, just so A is a G0 submodule of G1, so it is something not an ideal, a little less. with the property that G1A is contained in A implies so this is the property. So for all A non-zero that are G0 submodules such that G1 bracket G1A is contained in A, then the bracket of G1 and A is G0. We will see how it works for SL. This is a strange property. So G1 is a faithful G0 module, and the bracket G0 G1 is equal to G1. Okay. So this is the very strange thing. So what we really need is the arrow that says if this is true, then it is simple, because that's what we need, right? Fabrizio, you're not happy with the proof?
No, I'm just looking at the
No, because then I need
strange.
you. Because, so, this arrow I can do. This arrow, 1, 2, 3 implies simple, I can do. The other arrow, if it is simple, then it has all of these properties. Mousson makes some claims, and then I will give you the claims as exercise. Because I don't want to say I don't know how to do it. It's that I did not prepare to, you know, I was in Luxembourg for last week. It was just is an unprepared professor. So the problem with this chalk is very bad, and then after you have written on the board, it will not erase. This is the time I will buy chalk. Or I could get it from physics department where they are less cheap than us and they buy decent chalk. I could go there and steal some. No, Fabrizio, you are not happy.
I don't know, because in the first point,
But
so if G1A is contained G0
cosa ho fatto?
is
Aspetta.
equal G0,
Non mi
it means
agitare.
that
Dove ho
G1
sbagliato?
G0 is contained in A.
No, ma mi stai agitando.
No, but it's
No.
just strange.
Okay, let me give the proof, then we can comment. Because if it works, right, we can...
Okay. Yes.
No, I have to confess that all of this time working on simple Lie superalgebras, I never really sit down and prove that they were simple. You see what I mean? I mean, you take a granted, okay, they're simple, fine. It is good to stop and reflect on this. So is this the first time I'm reflecting on this? So it's...
I'll tell you what is strange. In the first point, you have G1 bracket G1A contained in A. But then, if this is true, then G1A is G0. So let's go back to the first bracket. We have G1, G0 contained in A.
Yes,
And then in point 3, you have G0, G1 equal G1.
yes,
So this means that A is G1.
yes.
Is this...
I don't see a problem.
So it means that the only A you can choose is G1 itself,
Yes.
in point 1. Okay.
Because Mousson wants to give you an operative trick to do this, right? No. No.
So this means
No,
G1
it is a no.
irreducible.
No, you can take a reducible. G1 it can be a sum of... In fact, we will show for SLMN that G1 is the sum of 2 irreducible, and each of the 2 irreducible can be chosen as this A. If A is irreducible, it will work, right? Because suppose that the G0 there is G1 plus. This tells you only the whole G1, but there could be a submodule, say G1 plus, And then this condition, this A could be G1 plus, right?
No, because you have a G1.
Faithful
A-
G0 module means just that G0.
Oh, okay, go on. It's just fine.
No, I agree this strange. Then I will explain the other error, because the other error I couldn't do. So let's assume these three are true. I think it will be useful to see the example of SLM, because then it will be clear what this G1 can be. And it's not always irreducible, that's the point. Okay, so we have to prove that G simple it means it is not abelian, and maybe we should assume it's not abelian, right? So it's not abelian because if it were abelian, then G0 will act trivially on G1, so we exclude this case.
Sorry, can you repeat? I just know.
No, because if G is abelian,
Okay.
then all the brackets are 0, so we assume it's not abelian, then we take an ideal and we show the ideal is either G0 or, so take I inside G ideal, and then we have to prove a question I is 0 or I is G. That is the question. Okay, this ideal is, of course, it has an even and an odd part that will split into two parts. They're disjoint, of course. Then, so if if the odd part is not there, we try to reach a contradiction. So, and I0 is non-zero. So we have the following situation that I0 G1 ecco, mi scassa la dimostrazione, ma va bene.
No,
Ma come faccio? Scusa, sono qua tutta felice. Cosa c'è?
But the fact that I is homogeneous is always true, or is by definition? It's
Sì, we take homogeneous, yes.
That's an important one.
Yes,
So in the definition of simple, you
I want homogeneous
no
ideas.
trigger of homogeneous.
Or is it true that any ideal is a direct sum of its homogeneous components?
Io che
You
so.
want, but all of this is everything.
No, Yes, at the end it will turn out to be homogeneous. But the question I'm raising is that if you have a non-homogeneous ideal, can you...
Decompose it as direct sum of
maybe
homogeneous
not.
components?
No.
No, by
No.
definition, it's not homogeneous.
Yeah.
Okay, not
No, it's in this... I think it's in this
Whatever
theory.
it is.
Yes. No, you are right. It's like when I didn't say the bracket is preserving the homogeneous component. You remember you asked this
Yeah.
question. So all the objects here are always inside the category of Z2 graded. So, right? I think no, right.
In the simple Lie superalgebra, you may have some
Yes, that is-
non-trivial idea, but it must be.
This I would not, yeah, I would not expose about
It's
this
important.
because no, I see what I see what you mean, but I'm not sure. So I'm not sure that the fact that you grant the existence of homogeneous may imply that there are no. You see what I mean? I don't know this. You have to come up with a counter example.
The
You
clear,
promise me. Eh?
clear,
Yes, the strange.
clear.
Strange. Let's call them strange.
It's better. It's better to call them strange.
Oh,
No, because it's a derogatory term in English. No, it's a mathematical term, unfortunately is used. In Italy we have the same, right? There are words that are perfectly common words, but unfortunately are used in so we call them strange. P and Q, right? So they will have ideals that are...
it's so cute.
I was planning to do the strange next time. Let me
Okay.
figure this out. No, but I will...
Okay,
When I'm studying the stranger for the exposition, I will try to find ideas that are is a good idea. Then we get okay, so it's so we have that. So this is to be contained in I1 because we're taking the component 0 times G1. It has to be contained in I1, but I1 is 0 because we are doing this. So this is the first step. If I1 is 0, but then you see the point is that. This forces I0 to be 0 itself because we have it is a faithful G module, right? So the only bracket, we know what faithful means, right? There are no elements in the G0 that bracketed with all G1 give you 0. So this implies, by the property 2, that this is I0 is 0. So this first case where we give hypothesis that I1 is 0 will give us what we want. Okay? Are we sort of right? So the second case, so we take I1 no 0, and then we apply to I1 this, we take I1 equal to A. So this is a G0 submodule of G1. So the property 1, take I1 equal to A. So let us, so certainly it is a G0 submodule. Then if I take I1, so G1, so it is G1. So if I take the bracket of G1 by I1, what do I notice? I notice that this sits inside I0 because this is an ideal, right? This sits in I0. And then if I do the bracket of I1, I0, it will sit inside I1 because it's an ideal again. So it will satisfy this property.
So you have A there, not G1.
Ah, sono stata disastrosa.
No, it's a mistake here.
So it is, sorry. No, it's G1, because if I do G1 times 0, it is an ideal as 0, so it will sit, I'm sorry. No, vabbè, ma adesso you will see how strange, because the hard part is this one, but we don't need, luckily. So, what does he say? He says that by the property 1, that G1 I0, right? No, G1 I1 is equal to G0. Okay. Okay. And this means, in particular, you see, because G1 I1 is an element of the ideal, because of property of ideal. So this tells me that this has to be I0, right? Because it has to be inside the ideal. Marta not happy.
No,
Ideal means that
I0 is contained in G0.
yes, the
Why
property.
equal?
Okay, property 1 tells me that G1A is equal to G0. This is the property, right? Now, so I conclude this fact, but I remember that I1 is in an ideal. So this means that when you bracket G1, you have to go in the ideal and you are forced to go into the I0 because of homogeneity. So G0 is equal to I0, but then G0, G1, I continue here. So G0, what do you want to say? So this is the ideal I0. So G0, so this has to be inside I1. So wait, this This is
equal to G1 by 3.
right, thank you, because I said it's obvious here, so I didn't see. So by the property 3, this is equal to G1, and then G1 has to be equal to I1. And so we conclude. So the case where I1 is 0 gives the ideal equal to 0. The case I1 non-zero gives the ideal all G. So this is an effective criterion to establish when a superalgebra is simple. Now, the other way around, I will not prove because I said it's just lack of preparation, but not just lack of preparation. I got upset because I couldn't do. I tried, I couldn't do. Then I said, okay, if I cannot do, I get upset. So let me make a comment on the part that we don't need. But Mousson claims it is true. But now Fabrizio will humiliate me by discovering immediately. No, but it's something stupid that is escaping me, I know, because Mousson says it's obvious. So what upsets me, he says it's obvious. While he devotes some time to do this, he will give this argument, which is an argument that you really don't have to give, right? Because one could figure it out. This is not so hard. And the other one, he says, is obvious. So this is what upsets me. Why? This one you give that is simple, the other one you say it's obvious and I don't get it. I don't understand.
Sometimes they are false.
They're false, in fact. There is this possibility.
It's so obvious. Sometimes happens.
No, I remember when I was in Torino, I listened to the conference of Alain Cohn, the field medalist, that he wrote a paper, and then at some point he needed the result in that paper. And so he was like, I really needed that result because I needed to know whether it was true or not, because it was important. There was some contradiction to the theory. So he went to his paper and the paper said, it is obvious. It took him a month, 8 hours work every day to verify this. So then he was telling us that, no, 8 hours of a field medal for a month to verify the obvious statement. So he said, you know, and now I'm more careful. It is obvious. It's interesting, isn't it? I found it very instructive, this little story. So it was true at the end. It was there. Okay, so assume it is simple. He makes the following claim. He defines 3. So he defines, we don't need this, but let's do this. So the element in G0, which so we're looking at the elements on G0 that act trivially with bracket on G1. Now it is clear that this B cannot exist because if G1 is a faithful G0 module, this B will have to be 0, right? So to prove B equals 0, this is the contento. This is equivalent to the property 2. And the way he does it is by claiming this B is an idea of G0. Because G0, wait, we don't know G0 is simple, wait a second. No.